In astronomy, the main sequence is a continuous and distinctive band of stars that appears on plots of stellar color versus brightness. These color magnitude plots are known as Hertzsprung Russell diagrams after the co-developers, Ejnar Hertzsprung and Norris Russell. Stars on this band are known as main sequence stars or dwarf stars. After a star has formed, it generates thermal energy in the dense core region through nuclear fusion of hydrogen atoms into helium. During this stage of the star's lifetime, it is located along the main sequence at a position determined primarily by its mass, but also based upon its chemical composition and other factors. All main sequence stars are in hydrostatic equilibrium, where outward thermal pressure from the hot core is balanced by the inward pressure of gravitational collapse from the overlying layers. The strong dependence of the rate of energy generation in the core on the temperature and pressure helps to sustain this balance. Energy generated at the core makes its way to the surface and is radiated away at the photosphere. The energy is carried by either radiation or convection, with the latter occurring in regions with steeper temperature gradients, higher opacity, or both. The main sequence is sometimes divided into upper and lower parts, based on the dominant process that a star uses to generate energy. Stars below about 1.5 times the mass of the Sun primarily fuse hydrogen atoms together in a series of stages to form helium, a sequence called the proton-proton chain. Above this mass, in the upper main sequence, the nuclear fusion process mainly uses atoms of carbon, nitrogen and oxygen as intermediaries in the CNO cycle that produces helium from hydrogen atoms. Main sequence stars with more than 2 solar masses undergo convection in their core regions, which acts to stir up the newly created helium and maintain the proportion of fuel needed for fusion to occur. Below this mass, stars have cores that are entirely radiative with convective zones near the surface. With decreasing stellar mass, the proportion of the star forming a convective envelope steadily increases, whereas main sequence stars below 0.4 m undergo convection throughout the mass. When core convection does not occur, a helium-rich core develops surrounded by an outer layer of hydrogen. In general, the more massive a star is, the shorter its lifespan on the main sequence. After the hydrogen fuel at the core has been consumed, the star evolves away from the main sequence on the HR diagram. The behavior of a star now depends on its mass, with stars below 0.23 m becoming white dwarfs directly, whereas stars with up to 10 solar masses pass through a red giant stage. More massive stars can explode as a supernova, or collapse directly into a black hole. History. In the early part of the 20th century, information about the types and distances of stars became more readily available. The spectra of stars were shown to have distinctive features, which allowed them to be categorized. Annie Jump Cannon and Edward C. Pickering at Harvard College Observatory developed a method of categorization that became known as the Harvard Classification Scheme, published in the Harvard Annals in 1901. In Potsdam in 1906, the Danish astronomer Ejnar Hertzsprung noticed that the reddest stars, classified as K and M in the Harvard scheme, could be divided into 2 distinct groups. These stars are either much brighter than the Sun, or much fainter. To distinguish these groups, he called them giant and dwarf stars. The following year he began studying star clusters, large groupings of stars that are co-located at approximately the same distance. He published the first plots of color versus luminosity for these stars. These plots showed a prominent and continuous sequence of stars, which he named the main sequence. At Princeton University, Norris Russell was following a similar course of research. He was studying the relationship between the spectral classification of stars and their actual brightness as corrected for distance, their absolute magnitude. For this purpose he used a set of stars that had reliable parallaxes and many of which had been categorized at Harvard. When he plotted the spectral types of these stars against their absolute magnitude, he found that dwarf stars followed a distinct relationship. This allowed the real brightness of a dwarf star to be predicted with reasonable accuracy. Of the red stars observed by Hertzsprung, the dwarf stars also followed the spectral-luminosity relationship discovered by Russell. However, the giant stars are much brighter than dwarfs and so do not follow the same relationship. Russell proposed that the giant stars must have low density at great surface brightness, and the reverse is true of dwarf stars. The same curve also showed that there were very few faint white stars. In 1933, Bengt Strömgren introduced the term Hertzsprung-Russell diagram to denote the luminosity spectral class diagram. This name reflected the parallel development of this technique by both Hertzsprung and Russell earlier in the century. As evolutionary models of stars were developed during the 1930s, it was shown that for stars of a uniform chemical composition, a relationship exists between a star's mass and its luminosity and radius. That is, for a given mass and composition, there is a unique solution for determining the star's radius and luminosity. This became known as the Vogt-Russell theorem, named after Heinrich Vogt and Henry Norris Russell. By this theorem, when a star's chemical composition and its position on the main sequence is known, so too is the star's mass and radius. A refined scheme for stellar classification was published in 1943 by W. W. Morgan and P. C. Keenan. The MK classification assigned each star a spectral type based on the Harvard classification and a luminosity class. The Harvard classification had been developed by assigning a different letter to each star based on the strength of the hydrogen spectral line, before the relationship between spectra and temperature was known. When ordered by temperature and when duplicate classes were removed, the spectral types of stars followed, in order of decreasing temperature, with colors ranging from blue to red. The sequence O, B, A, F, G, K and M. The luminosity class ranged from I to V, in order of decreasing luminosity. Stars of luminosity class 5 belonged to the main sequence. Formation. When a protostar is formed from the collapse of a giant molecular cloud of gas and dust in the local interstellar medium, the initial composition is homogeneous throughout, consisting of about 70% hydrogen, 28% helium and trace amounts of other elements by mass. The initial mass of the star depends on the local conditions within the cloud. During the initial collapse, this pre-main sequence star generates energy through gravitational contraction. Upon reaching a suitable density, energy generation is begun at the core using an exothermic nuclear fusion process that converts hydrogen into helium. When nuclear fusion of hydrogen becomes the dominant energy production process and the excess energy gained from gravitational contraction has been lost, the star lies along a curve on the Hertzsprung-Russell diagram called the standard main sequence. Astronomers will sometimes refer to this stage as zero-age main sequence, or ZAMS. The ZAMS curve can be calculated using computer models of stellar properties at the point when stars begin hydrogen fusion. For this point, the brightness and surface temperature of stars typically increase with age. A star remains near its initial position on the main sequence until a significant amount of hydrogen in the core has been consumed, then begins to evolve into a more luminous star. Thus, the main sequence represents the primary hydrogen burning stage of a star's lifetime. Properties. The majority of stars on a typical HR diagram lie along the main sequence curve. This line is pronounced because both the spectral type and the luminosity depend only on a star's mass, at least a 0th order approximation, as long as it is fusing hydrogen at its core, and that is what almost all stars spend most of their active lives doing. The temperature of a star determines its spectral type via its effect on the physical properties of plasma in its photosphere. A star's energy emission as a function of wavelength is influenced by both its temperature and composition. A key indicator of this energy distribution is given by the color index B-V, which measures the star's magnitude in blue and green-yellow light by means of filters. This difference in magnitude provides a measure of a star's temperature. Dwarf terminology. Main sequence stars are called dwarf stars, but this terminology is partly historical and can be somewhat confusing. For the cooler stars, dwarfs such as red dwarfs, orange dwarfs, and yellow dwarfs are indeed much smaller and dimmer than other stars of those colors. However, for hotter blue and white stars, the size and brightness difference between so-called dwarf stars that are on the main sequence and the so-called giant stars that are not becomes smaller. For the hottest stars it is not directly observable. For those stars the terms dwarf and giant refer to differences in spectral lines which indicate if a star is on the main sequence or off it. Nevertheless, very hot main sequence stars are still sometimes called dwarfs, even though they have roughly the same size and brightness as the giant stars of that temperature. The common use of dwarf to mean main sequence is confusing in another way, because there are dwarf stars which are not main sequence stars. For example, a white dwarf is the dead core of a star that is left after the star has shed its outer layers. That is much smaller than a main sequence star, roughly the size of Earth. These represent the final evolutionary stage of many main sequence stars. Parameters. By treating the star as an idealized energy radiator known as a blackbody, the luminosity L and radius R can be related to the effective temperature Tf by the Stefan-Boltzmann law, where sigma is the Stefan-Boltzmann constant. As the position of a star on the HR diagram shows its approximate luminosity, this relation can be used to estimate its radius. The mass, radius and luminosity of a star are closely interlinked, and the respective values can be approximated by three relations. First is the Stefan-Boltzmann law, which relates the luminosity L, the radius R and the surface temperature Tf. Second is the mass-luminosity relation, which relates the luminosity L and the mass m. Finally, the relationship between m and r is close to linear. The ratio of m to r increases by a factor of only 3 over 2.5 orders of magnitude of m. This relation is roughly proportional to the star's inner temperature T, and its extremely slow increase reflects the fact that the rate of energy generation in the core strongly depends on this temperature, whereas it has to fit the mass-luminosity relation. Thus, a too high or too low temperature will result in stellar instability. A better approximation is to take epsilon equals Lm, the energy generation rate per unit mass, as epsilon is proportional to Ti15, where T is the core temperature. This is suitable for stars at least as massive as the Sun, exhibiting the CNO cycle, and gives the better fit Rm 0.78. Sample parameters. The table below shows typical values for stars along the main sequence. The values of luminosity, radius and mass are relative to the Sun, a dwarf star with a spectral classification of G2V. The actual values for a star may vary by as much as 20 to 30% from the values listed below. Energy generation. All main sequence stars have a core region where energy is generated by nuclear fusion. The temperature and density of this core are at the levels necessary to sustain the energy production that will support the remainder of the star. A reduction of energy production would cause the overlaying mass to compress the core, resulting in an increase in the fusion rate because of high temperature and pressure. Likewise, an increase in energy production would cause the star to expand, lowering the pressure at the core. Thus, the star forms a self-regulating system in hydrostatic equilibrium that is stable over the course of its main sequence lifetime. Main sequence stars employ two types of hydrogen fusion processes, and the rate of energy generation from each type depends on the temperature in the core region. Astronomers divide the main sequence into upper and lower parts, based on which of the two is the dominant fusion process. In the lower main sequence, energy is primarily generated as the result of the proton-proton chain, which directly fuses hydrogen together in a series of stages to produce helium. Stars in the upper main sequence have sufficiently high core temperatures to efficiently use the CNO cycle. This process uses atoms of carbon, nitrogen and oxygen as intermediaries in the process of fusing hydrogen into helium. At a stellar core temperature of 18 million Kelvin, the PP process and CNO cycle are equally efficient, and each type generates half of the star's net luminosity. As this is the core temperature of a star with about 1.5 m, the upper main sequence consists of stars above this mass. Thus, roughly speaking, stars of spectral class F or cooler belong to the lower main sequence, while A-type stars are hotter are upper main sequence stars. The transition in primary energy production from one form to the other spans a range difference of less than a single solar mass. In the Sun, a one solar mass star, only 1.5% of the energy is generated by the CNO cycle. By contrast, stars with 1.8 m or above generate almost their entire energy output through the CNO cycle. The observed upper limit for a main sequence star is 120 to 200 m. The theoretical explanation for this limit is that stars above this mass cannot radiate energy fast enough to remain stable, so any additional mass will be ejected in a series of pulsations until the star reaches a stable limit. The lower limit for sustained proton-proton nuclear fusion is about 0.08 m or 80 times the mass of Jupiter. Below this threshold are substellar objects that cannot sustain hydrogen fusion, known as brown dwarfs. Structure. Because there is a temperature difference between the core and the surface, or photosphere, energy is transported outward. The two modes for transporting this energy are radiation and convection. A radiation zone, where energy is transported by radiation, is stable against convection and there is very little mixing of the plasma. By contrast, in a convection zone the energy is transported by bulk movement of plasma, with hotter material rising and cooler material descending. Convection is a more efficient mode for carrying energy than radiation, but it will only occur under conditions that create a steep temperature gradient. In massive stars, the rate of energy generation by the CNO cycle is very sensitive to temperature, so the fusion is highly concentrated at the core. Consequently, there is a high temperature gradient in the core region, which results in a convection zone for more efficient energy transport. This mixing of material around the core removes the helium ash from the hydrogen burning region, allowing more of the hydrogen in the star to be consumed during the main sequence lifetime. The outer regions of a massive star transport energy by radiation, with little or no convection. Intermediate mass stars such as Sirius may transport energy primarily by radiation, with a small core convection region. Medium-sized, low-mass stars like the Sun have a core region that is stable. permeable against convection, with a convection zone near the surface that mixes the outer layers. This results in a steady buildup of a helium-rich core, surrounded by a hydrogen-rich outer region. By contrast, cool, very low-mass stars are convective throughout. Thus the helium produced at the core is distributed across the star, producing a relatively uniform atmosphere and a proportionately longer main sequence lifespan. Luminosity color variation. As non-fusing helium ash accumulates in the core of a main sequence star, the reduction in the abundance of hydrogen per unit mass results in a gradual lowering of the fusion rate within that mass. Since it is the outflow of fusion-supplied energy that supports the higher layers of the star, the core is compressed, producing higher temperatures and pressures. Both factors increase the rate of fusion, thus moving the equilibrium towards a smaller, denser, hotter core producing more energy, whose increased outflow pushes the higher layers further out. Thus, there is a steady increase in the luminosity and radius of the star over time. For example, the luminosity of the early Sun was only about 70% of its current value. As a star ages, this luminosity increase changes its position on the HR diagram. This effect results in a broadening of the main sequence band because stars are observed at random stages in their lifetime. That is, the main sequence band develops a thickness on the HR diagram. It is not simply a narrow line. Other factors that broaden the main sequence band on the HR diagram include uncertainty in the distance to stars and the presence of unresolved binary stars that can alter the observed stellar parameters. However, even perfect observation would show a fuzzy main sequence because mass is not the only parameter that affects a star's color and luminosity. Variations in chemical composition caused by the initial abundances, the star's evolutionary status, interaction with a close companion, rapid rotation, or a magnetic field can all slightly change a main sequence star's HR diagram position, to name just a few factors. As an example, there are metal-poor stars that lie just below the main sequence and are known as subdwarfs. These stars are fusing hydrogen in their cores, and so they mark the lower edge of main sequence fuzziness caused by variance in chemical composition. A nearly vertical region of the HR diagram, known as the instability strip, is occupied by pulsating variable stars known as Cepheid variables. These stars vary in magnitude at regular intervals, giving them a pulsating appearance. The strip intersects the upper part of the main sequence in the region of Class A and F stars, which are between 1 and 2 solar masses. Pulsating stars in this part of the instability strip that intersects the upper part of the main sequence are called delta-STScI variables. Main sequence stars in this region experience only small changes in magnitude, and so this variation is difficult to detect. Other classes of unstable main sequence stars, like beta-STScI variables, are unrelated to this instability strip. Evolutionary tracks. When a main sequence star consumes the hydrogen at its core, the loss of energy generation causes its gravitational collapse to resume. Stars with less than 0.23 m are predicted to directly become white dwarfs when energy generation by nuclear fusion of hydrogen at their core comes to a halt. In stars between this threshold and 10 m, the hydrogen surrounding the helium core reaches sufficient temperature and pressure to undergo fusion, forming a hydrogen-burning shell. In consequence of this change, the outer envelope of the star expands and decreases in temperature, turning it into a red giant. At this point, the star is evolving off the main sequence and entering the giant branch. The path which the star now follows across the HR diagram to the upper right of the main sequence is called an evolutionary track. The helium core of a red giant continues to collapse collapse until it is entirely supported by electron degeneracy pressure, a quantum mechanical effect that restricts how closely matter can be compacted. For stars of more than about 0.5 m, the core eventually reaches a temperature where it becomes hot enough to burn helium into carbon via the triple alpha process. Stars with more than 5 to 7.5 m can additionally fuse elements with higher atomic numbers. For stars with 10 or more solar masses, this process can lead to an increasingly dense core that finally collapses, ejecting the star's overlying layers in a Type II supernova explosion. Type Ib supernova. A Type IC supernova, when a cluster of stars is formed at about the same time. The lifespan of these stars will depend on their individual masses. The most massive stars will leave the main sequence first, followed steadily in sequence by stars of ever lower masses. Thus the stars will evolve in order of the position on the main sequence, proceeding from the most massive at the left toward the right of the HR diagram. The current position where stars in this cluster are leaving the main sequence is known as the turn-off point. By knowing the main sequence lifespan of stars at this point, it becomes possible to estimate the age of the cluster.